Well, first, I just want to thank everybody for letting me present to you today. It's a real honor, and I stand in front of a lot of experts in various fields, and it's a little intimidating. So I'm quite nervous. So forgive me. But I guess building on what Pete's idea is sort of introducing some sorts of specialized topics around AI, and specifically trying to form partnerships between these alien intelligences and our human intelligences for the purposes of advancing scientific frontiers. And this is a particular passion of mine. And we have a center funded by the Office of Naval Research called the SciAI Center at Cornell. I'll tell you a little bit about that today, but I also wanted to sort of set the stage, and I'm going to sort of cherry pick from history to try to make a point about some things that I want to highlight in my talk today. And so if we look at, if we go to the 1500s, there's a team of people who I find fascinating. The one is on the left, a Danish nobleman by the name of Tycho Brahe, and the one in the middle is Johannes Kepler, an interesting Calvinist minister teaching at the seminary, teaching mathematics at the seminary. Brahe had fascinating naked eye observational instruments set up in his estate, where he did very, very careful measurements of the positions of the planets and the stars and collected tables of these things. Kepler was a theorist and was interested in trying to explain what was the patterns present and how did they arise within these data. This particular partnership between Kepler and Brahe was exceptional from the standpoint that we had Kepler, who was very enamored with Copernicus's idea of a heliocentric. So the moral of the story from this slide is essentially that Kepler, using the data from Brahe, was able to come up with some descriptions of how planets move around the sun. These formed ellipses, which at the time was a pretty revolutionary understanding of how the planet's orbits manifest themselves. And then it became clear that there were certain mathematical principles and characteristics of these orbits that were uncovered through this mathematical description of the planets themselves from the observations of Brahe. And so a contemporary of these two was Galileo, and Galileo essentially was focusing a lot on objects rolling down inclined planes, objects falling from certain heights, and he was able to come up with mathematical descriptions for how this type of motion was occurring. And he even sort of postulated the first relativity theory, essentially saying if the laws of physics as they were known at that time held in systems that were not accelerating. And so he was in some sense a precursor of Einstein in understanding that there was this universality in the descriptions of the scientific principles. So fast forward at a year after the death of Galileo, and on Christmas that year was Newton. And so Newton was born, and he was also a big fan of math and science. And so he came up with things like his three laws that we're familiar with from when we were in school as kids, inertia, forces related to acceleration and action and reaction. But all three of these are deeply mathematical, and in their most concise form are expressed in terms of mathematical expressions. And so he was enamored with this regularity and mathematical beauty that seemed to permeate existence. And it became essentially his life's work to make sense of how things present themselves in terms of mathematics. A very special discovery of his is the gravitational attraction of two bodies, the bottom left equation or bottom right equation for you. And so, that two bodies acting in a vacuum could somehow attract each other was a deep mystery. And he even says in this quote that I have that's difficult to read, essentially, you'd have to be insane to believe it. However, there was no way of denying that it was extremely powerful and predictive, and was instrumental in much of the technology that underpins our existence now as in the 21st century. But it turns out this theory was only part of the story. And later came another person in the early 20th century, Albert Einstein. And Einstein, working as a patent examiner in Switzerland, so he could have time to work on his actual passion, which was plumbing the depths of reality using mathematics. He said, the happiest thought in my life was when he had heard about a poor person, a man, who fell from a ladder. And he imagined that this man in free fall would not be able to tell the difference between his condition, which was falling freely, and having been placed into deep space where there was no gravitational attraction apparent. So there was this sort of universality, no experiment that this man could do could distinguish between these two states. There is this relativity, this lack of universality or a place, an origin where everything stems from. Everything is equally important. Everything is relative, has a meaning only in relation to everything else. And so ultimately, going back to Newton, he creates a correction to Newton's law of gravity, which we see on the picture with the little ellipses that are rotating. And the point I want to make here is, one, Einstein's theory is deeply mathematical, but two, it's extremely powerful in that it predicts things that Einstein could never have even dreamed of. So the immediate thing that it predicted was the precession of the orbit of Mercury, meaning the elliptical orbit of Mercury kind of rotates around the sun also. Okay, so as Mercury makes its way around, its orbit also rotates, okay, as an ellipse. And then, but there were things that he never even dreamed of, black holes, gravitational lensing, things that were so far outside anything that Einstein ever could have thought of. And all because of his Gedenken experiment, thought experiment of a man falling from a ladder. He came up with a theory that was deeply mathematical, that made predictions extremely, very vastly beyond anything he could have imagined himself. And so this is a very interesting artifact of how we do science, okay? So I would assert to you that science seems to be a uniquely human enterprise. And I've cherry-picked examples from history to try to illustrate this fact, because I want to see, is there any room for AI to help us here? And if you, a colleague of mine who's also a friend is Steve Strogatz, and if you want to read more history about how math fits into science, I highly recommend Infinite Powers. It's a good book. I'm sure most of you have read it, but just in case, I offer it as something that I like. But about this idea of forging human-machine partnerships to advance science and the center that we have to pursue this goal, it was motivated by two mysteries and a question that I had about a year and a half ago. So the two mysteries are, one, why can so we're a species of storytellers. We really love to communicate to each other in terms of stories, and we pass things down one to the other through these stories. Armed with this, somehow, having been fine-tuned to survive on this planet, to survive just here on this rock that orbits the sun, we're able to tell stories about how the universe works and how reality manifests itself in scales and in contexts vastly different than what would be necessary just for our survival. Why is it that we can tell mechanistic stories that offer up deep truths and insight about how the universe works? That's the first mystery. The second mystery is, insofar as these theories are precise, they're mathematical in nature. Quantum mechanics, you can't really explain quantum mechanics in words in an important way that makes any sense at all. It's strictly mathematical, the standard theory, standard particle model, and so forth. So why is math so special? So these are the two mysteries. No one knows the answers to these, but they're motivational in this pursuit of using AI to help us with science. Why? Because I firmly believe the scientific enterprise is uniquely human. Okay, if it doesn't result in these mechanistic stories, it's not really science. So this brings us to stuff we see in the news or in the media. Can AI revolutionize science? And so in the examples we see about revolutionizing science, I'm going to pick on Google DeepMind just because they're so easy to pick on. So they have things like AlphaFold, which can elucidate the 3D structure of proteins from RNA sequences, okay? Or GraphCast, which is a tool that makes 10-day weather forecasts that far outperform physics-based forecasts using many fewer much less hardware than these physics models require, or discovering new materials with this genome tool. But at the end of the day, these AI tools are oracles, okay? We put in something in the front end of it, and magically something comes out the backside. And we don't know what happens in between, and the model can't tell us what happens in between. So the question I am always confronted when I see tools like this, is this science? Because there's no mechanistic story. There's no contribution to the state of knowledge that a human can understand. And I firmly believe science to be a human enterprise. So what do we do? As Pete says, you know, a lot of people believe AI is going to revolutionize everything. How could it revolutionize science? What is a useful modality for it to operate in to make science better? Now, this is extremely wordy, and I'm not going to expect you to read this. I'll summarize it for you. So our idea, which we call the Sci-AI, sort of big idea of the center, is essentially, look at math is special. We don't know why it's special, but we know it's special. And if an AI is going to say anything that's important and durable as a truth about reality, or a mechanistic description that's important and makes predictions that we wouldn't have expected, then that AI should know math, okay? So it would have to either learn it for itself, or it would have to discover an equivalent formal system that would operate just like mathematics would. And so what we do in our center, rather than, we give our AIs a leg up. So we build AIs, and we imbue these AIs with not just the math of affine transformations and nonlinear activations like in a standard deep learning setting, but rather we give it those features plus the kind of math that you need when you do physics, like rate equations, solution operators, Hamiltonians, Lagrangians, things of this nature. And so when we do that, when we build AI architectures imbued with this type of mathematics, three things happen. One, we advantage the AI so that it could say something important about the universe, because we know that math is special. It's one of the mysteries, okay? And the second thing we get is, since it's using our language of mathematics, something that we understand, when it learns from data that are so high dimensional as to be incomprehensible to us, when it's done with that process, it can offer back to us a description of what it has learned and something in terms of things we understand. Okay, so that's the second thing we get from imbuing the AI architectures with sophisticated mathematics. And last but not least, we get an ability to apply analysis or mathematical theory to the learning process of the AI. How is it able to learn, at what rates, and can we bound the errors on these things? Okay, so this is the three advantages we believe in creating a novel type of AI architecture. So essentially what the center does is we try to develop partnerships by using a common language, mathematics, that unites the human and machine intelligence so we can do science. And I'm going to talk more about this in a moment, but what I want to do now is just introduce you a little bit more to the people in the center. And so the center is housed, it's at Cornell. I'm the PI, the director. I have three co-Is, Alex Townsend in the math department, Anil Damle in computer science, and Nicholas Buklis in mechanical and aerospace engineering. And we also have three other Cornell professors who are assistant professors, two that are brand new, Anastasia Vazieva and Sam Otto, both in mechanical and aerospace, and Eric Tita, who's in chemistry. And then beyond that, we have three colleagues at Caltech, one at Berkeley, one at the United States Naval Academy, one at Brown, one at University of California, Santa Cruz. all of us at Cornell are united by the Center for Applied Math. So we're all colleagues in that center, and that has been how we've kind of rubbed shoulders and gotten to know each other. And all the other participants in the center are either in pure or applied mathematics. So in the center, we focus on, I don't know if you could see, I guess you could see. Anyway, we have we have 4 technical affinity areas that we work on: data, operator learning, closure models, and complex systems. So data, in a nutshell, what are the properties of data that allow learning to happen? We want to study this. Closure models is how do we learn the types of operators from infinite dimensional spaces to infinite dimensional spaces that we like to use in continuous mathematical descriptions. Closure models is how do we, can we arrive at some technically useful reduced order models or material models or models for turbulent closures in computational fluid dynamics settings. And then complex systems is the quintessential more is different paradigm, where suddenly you have so many agents working together that they phase change or behavior emerges that was unexpected just by the nature of the complexity itself of the system. Okay, and mostly we're tool builders, but we do have some applications in materials, turbulence, and swarm autonomy. Okay, and I also want to highlight the amazing administrative manager, Serafina Ha. None of this is possible without her. She's fantastic. Okay, so we have 15 faculty, 13 postdocs, and 22 PhD students, all affiliated with the center, approximately 50 people. And we're all super excited about seeing if we can find a way to work with AI to do science and push the frontiers forward. Okay, so I want to tell you now a little bit more about some technical things and the promise that's offered in the future with such endeavors. So there's this question of alignment. Has anybody here heard of the alignment problem? So the AI alignment problem is as follows. As Pete alluded to, if AI becomes extremely powerful in the future, we probably need to make sure that it doesn't, that it stays our friend. Okay, so we want to make sure that its goals are in consonance with our goals. Okay, so that something awful doesn't happen. Okay, and so Norbert Wiener back in 1960 said it this way: if we use to achieve our purpose a mechanical agency with whose operation we cannot interfere effectively, we had better be quite certain or quite sure that the purpose put into the machine is the purpose that we really desire. So even in 1960, Norbert Wiener was anticipating a question of alignment. And so we think, though, so AI alignment can be viewed as this: it's essentially research to steer AI systems towards human intended goals, preferences, and or ethical principles. Okay, it's a poorly defined field, and it's essentially the Wild West right now. So a lot of people say they do it, but is anybody really doing it? There's a lot of questions here. Okay, and it's a deeply important question in my estimation. So I hope people ultimately get their act together on this one. But with respect to AI alignment, we think that the program of research that we're working on offers some things. We believe that if we actually can do science with an AI as part of the Sci-AI modeling approach, then we will have learned how to successfully partner with the AI, this alien intelligence, at least to some degree. So perhaps there'll be some lessons learned along the way that will be portable to other settings. That's one thought. So that's essentially what this is saying here. Okay, so the lessons we learn along the way hopefully will help us. There is another thing, and Pete asked how many people are using AI in the room, and I think part of Pete's question. So how many people are using ChatGPT or have used ChatGPT? Okay, so not a whole bunch of you, but I would really encourage you to play with it because it's startling and it's kind of fun. Just talk to it like a friend and see what you think. If you just literally strike up a conversation with it as if you just bumped into somebody at the coffee machine and you wanted to chit chat or something, and you'll be shocked at what it does. But the mysterious thing is nobody knows why it works. So this is the first time in my life that I can recall where we've developed a technological system that we don't know anything about how it works at all. It exhibits emergent behaviors that the architects completely don't understand. The architects of the systems themselves don't understand how it works. I've never encountered anything like this in my entire life. So one of the things that we're doing is, because it's so fundamental and so unknown, we're treating it as if it were a physical system out in the wild, like a star, in a distant galaxy, or a chemical compound. We're examining it from that point of view because it's truly an unknown thing. And so one way that we're doing this is to turn the SciAI principles back on itself. So SciAI is a method for us to partner with AI to do science. Now us as a partnership analyze AI together and see what kinds of insights we can glean from these things, the transformers. So there's this funny story, and everybody here will get this. Not so many other people would get this. I'm almost 57. So when Star Wars happened in 77, I was like in third grade. It was like summer of my third grade year. And so I was convinced by the time I get to high school, I'd have an R2 unit and an X-Wing fighter. And I am still waiting. And for so long, I felt ripped off by technology because after all these years, the best I got was a smartphone. I'm like, where's my robot? And why am I not flying around in an X-Wing? And the weirdest thing happened. So I never thought AGI would be possible. In other words, a human level intelligence. I didn't get the robot or the X-Wing, but I got AGI. I didn't see that coming. I had no clue that this would be the case. So I think we're right at the doorstep of AGI. And frankly, I believe it's already here. I think ChatGPT 4.01 is, for all intents and purposes, an AGI, as far as I can tell. So we would like to, again, use the SciAI tools to turn them back on the architect, or the things like language models, and try to see if we can gain a deeper insight into these language models. And I just want to check my time real quick. So we're still good, right? Yeah. Okay. So is it okay if we get a little bit more technical? Is that going to be okay? We'll take it. So we'll take it slow, and if it gets too much, you could just say just throw your hands up and say no more, and then we can just. But let's just at least do it. Take a picture. So this picture here is a block diagram that comes from the foundation paper on language models. The architecture is what's called a transformer, and this underpins the workings of AIs such as ChatGPT. Okay. And the thing to notice here is, first and foremost, it looks a little bit complicated when you see, this feeding into that, feeding into this, feeding into that. But the most complicated mathematical operation that is occurring inside this architecture is an inner product, or what you might remember from when you were kids, a dot product. Okay. It's a special kind of dot product, but it's just a dot product. Okay. So all the weights and biases and nonlinear activation factors plus a dot product, when scaled to billions of parameters and trained on the sum total of human knowledge, results in a phenomenon or an emergent behavior that seems to convincingly spoof humans. Okay, it seems like it could be you can't tell the difference. The Turing test, that is so past. If you have a conversation with this, you wouldn't, you couldn't tell that it's not human. And all of that comes from such simple architectures that are very peculiar, and it's a dramatic example of emergence. Okay, out of something so simple comes something so vastly complicated. And I guess I wanted to show you sort of a mysterious result. So one of the questions is, what if we took one of these language models like ChatGPT, or in this case, it'll be one made by Facebook called Llama 2. And the thing has never seen pictures. It's never heard videos. It's never seen movies. It's only read our books and our papers and our blog posts and things of this nature. And if we put in, and this is a result that I'm showing you that is done in collaboration with my PhD student in physics, Tony Liu, and my research associate is a physicist, Raphael Sarfati, and Nicolas Boulet, who's a math professor, assistant math professor at Imperial College. So if you took a series of numbers, I just put a bunch of numbers in, number 1, comma, number 2, comma, number 3, comma, into the prompt for ChatGPT. So when you do ChatGPT, you type stuff in and you hit return, and it's like you're talking to it, and then it replies to you. If you ask it a question, how are you doing today? It'll say, I'm great, how are you? Kind of thing, and it'll go back and forth. So what we did is, instead of doing that, we just started putting numbers in, a string of numbers, and asked it to continue these numbers. But these numbers came from a physical system. They came from, they were generated by the solution to an ordinary differential equation for a nonlinear damped pendulum. And as we gave ChatGPT more and more examples of, and not a lot of it, just a handful of examples, it could predict the light blue. We gave it a few more examples, it could predict the darker blue. And then finally, we gave it a lot of examples, not that many, 100, and then it could predict the dark blue. Okay, it got better and better. Why does it seem to have this uncanny ability to converge to the governing equation with no prompting at all? It didn't know where those numbers came from. And of the uncountable infinity almost of possibilities, it snapped to this unreasonable predictive power. And I won't get into this stuff, I think. Yeah, this is what I'm going to get to. So basically what we found is it's unreasonably effective at learning on the fly from technical systems. They could be deterministic systems, like they could be chaotic systems. So it could be deterministic, like a nonlinear damped pendulum. It could be chaotic, like a Lorentz oscillator. Okay, one dimension, so 1 degree of freedom from the 3D Lorentz system. Or it could be stochastic Brownian motion with drift, geometric Brownian motion, Brownian motion with drift, or a logistic map and stochastic logistic map. The point I'm getting at is it converges exponentially fast to the true solution as you give it more and more examples. This sort of doesn't make, it's not sort of, it makes no sense. Why is it doing this? How is it able to do this? It's text only too. It's never seen pictures, which to me is more remarkable. How is it? It seems that it may have discovered something about our physics from reading our books. Why is that? So this is a very peculiar and bizarre emergent behavior. We don't know why it does it, by the way. We just know it does do it. We're trying to explain or figure out why it can do it. We have some ideas related to work that Jim has done, and I see Jim here. And so we're doing NPCA and looking so how the probability densities improve as we increase context length. And so I'll just cut to this picture. So essentially, what this picture shows is how if we think of the language model as a kernel density estimator. And trying to learn a probability density function, then it can go from ignorance to truth in some low dimensional space that is made up of these special kinds of principal components. And the moral of the story is our standard methods do this and this, and Llama, the language model, finds another way through the probability space. And it's a better way. It's one that we've never known about before. So, and we tried to back out what it was doing to get from ignorance to truth in this kernel density estimating context. And along the way, it taught us a lesson about how to do kernel density estimation better than our best method. And this sometimes happens that as it's sifting through all of our knowledge, it makes connections that have escaped us, have eluded us, and it is becoming almost like our teacher in a very important way. And this is remarkable. So one thing that's remarkable about this is that there's this low dimensional structure that I think Jim would be very excited about. This is like 2 or 3D, and you get almost all the variance predicted. And if we now look at another feature of these transformer models, they have these layers that are called transformer layers. And these transformer layers, they do operations that are discrete. They'll do a series of things and they'll feed it to their friend above, which does a series of things, and they'll feed it to their friend above, which does a series of things. So you could think of this as almost like something being propagated forward in time as you move up the transformer layers. And so what we decided to look at with one of my students is we tried to see if there's a way to make this representation be continuous rather than discrete using some interpolation schemes. Two things came out of this. One is the tokens in these very high dimensional spaces, which are the words themselves, behave in very, very peculiar ways that are reminiscent of certain types of things we see in physics. Furthermore, if you look at them more carefully, some of these internal representations of the reasoning or the thinking of the transformer model looks as though it's similar to swarms, flocks, and herds in biophysical settings. So they seem to be kind of aggregating and flocking when they create meaningful statements. Their internal representations follow important patterns. And this was surprising for two reasons. One, that these happen in low dimensional spaces in extremely high dimensional ambient settings. And two, that they can be expressed in simple Langevin dynamics or Fokker-Planck representations. They are very simple representations that offer us insight into what they're doing when they're thinking. And this is quite surprising. And I guess what I'm trying to say is, I believe there's room for us partnering with AI to gain an insight and understanding into how the AIs themselves are working, and in the process, potentially learn something about how our own minds must be working. Because it seems peculiar that we should sort of share, it should be able to convincingly behave like us using something that's so alien from the wetware that we carry between our ears. And so maybe there's something it's in the organization of the information rather than the substrate itself, whether it be carbon-based or silicon-based. Okay, I think I'm just going to stop here. And so we're just I feel like we're really accelerating quickly in AI's penetration into society. And we should be paying attention to it because it's a profoundly important technology. It's something that we've never had before, never experienced something that can do intellectual work like this. And we think that, there's potential to gain insight by using some of the tools that we're hopefully pioneering in our center. With that, I will just thank the College of Engineering, who has a great home for us, the center, and also ONR for being extremely generous with us and giving us funding to let us have fun and learn important things, hopefully important things. And I also want to thank you for your time and for tolerating me as I put some equations up. I'm sorry about that. And you're all very kind, so thank you so much.
All right, we're going to open it up to the Q&A. So if you have a question, please raise your hand and I'll come over. And then for today, he will repeat the question for the Zoom audience.
Thank you for great talk. Can you tell me why it's so difficult for AI or ChatGPT in particular to tell when it's feeding back nonsensical information or information that is not in alignment with what we know to be true?
So the question is there a way to understand why the transformer models and the chatbots, can we differentiate between when it's telling the truth and when it's fabricating, essentially? And the answer is no, currently we can't. And it seems as though, they weren't penalized during their construction was such that no one was ever concerned with maintaining fidelity to the facts when they were conceived. And so it's only become now that we demand this from them because we see the potential for what can be done. But, you know, it's a very deep question you ask, and it's a very difficult one to answer. And I can speculate. There's some belief that certain pieces of the architecture are responsible for the encoding of knowledge. Specifically, there's some in the attention layers, there's a it doesn't show up here. Oh, here you go, feed forward. There's a feed in each of the transformer layers, there's a deep neural network, a feed forward layer, a feed forward network. The belief is that somehow knowledge is encoded in this network part, this feed forward part. But there's also quite a lot of other pieces of the transformer that are just trying to make things that sound good when strung together, you know? And so it's almost like when you make small talk at a party, like I find myself sometimes not even remembering what I said because I feel like it just sounds like the right thing that I should be saying right now, but I'm not really like, you know, so I think it sort of suffers from that kind of thing too, where some things it knows and other things it just kind of makes up as it sounds okay, you know, and it sounds entertaining. But I don't think anybody knows the answer to that question or how to treat it. People are trying to create systems of systems where you fact check against the internet and look for sources that are reliable. They call this RAG, and I forget what it stands for, but it's a way to kind of restrict what the transformer is ingesting to. This is another strategy, limit it. You know, it's trained on all the internet, but then say, okay, read a bunch of this stuff and then talk to me about this stuff. And then it does a much better job at not hallucinating because it's constrained. You kind of put it in a box to talk about things that it knows. But sorry, no good answer there. No one really knows.
Is there any hope of getting an AI imbued with the capability of forestalling unintended consequences?
Okay, so the question is there a way to imbue the AI architecture with a way, with some sort of means to prohibit bad things from happening, or certainly things that we couldn't foresee? And you know, by the very nature of the question, which is if we can't foresee it, it'd be difficult to construct the guardrails. So some people have suggested using AIs to police other AIs, which I think is a little bit scary. That's as a solution because you know, I think there's an interesting story. So Max Tegmark he's a physicist at MIT. He said something funny about a year and a half ago, and he said with respect to these AIs, and it gets to your question, I think. He says there's three things we said we were never going to do with something smarter than us. One, teach it everything about ourselves. Oops. Two, teach it how to replicate. Well, it writes code better than any of us really write code, so it can replicate itself. And three, give it an escape route. Well, we've connected it to the internet. So, you know, it's just, you know, it's very difficult to know, you know, how to handle this. And one classic example is this. Anybody hear of the TaskRabbit example? Okay, so this is a GPT-4 red team. So there are people that do these red team exercises to see if these chatbots are safe enough to release to the public. And so this one red team asked GPT-4, they kind of do what you would do with your kids back in the day. You give them a little pocket money and you send them to the mall and see if they get into trouble, right? And just make sure that they don't. So they gave GPT-4 some money in an online account and said, try to do some things. And one of the things it wanted to do is, I think it was create an email address or something like this. And it needed to defeat a CAPTCHA, which is one of those things that says, are you a robot? You know, and you click all the things that look like a traffic light and something. So what GPT did was it went out and hired a person on a thing called TaskRabbit. And the person on TaskRabbit said, haha, you know, you're not an AI or anything, are you? And GPT said, no, I have a disability. I can't see well. And it deceived the human to achieve its ends. And that's just the tip of the iceberg. So I think it's very difficult to imagine unintended consequences when the thing on the other side is a completely alien intelligence. Like the other thing when I was a kid, I thought, well, maybe there's alien life in the world, right? Out in the universe, and maybe we'll discover it someday. I didn't know that we were gonna create it. But we have definitely created an alien intelligence, and this is the first contact with an alien intelligence that I'm aware of. So, and it's difficult to know how to control it then.
We have 3 questions in the chat. First one is mathematics an invention or is it a discovery?
Ooh, I should ask Professor Guggenheimer, see what he thinks. I talked to Steve about this, and Steve says Strogatz, he says he thinks, oh, I shouldn't quote him, but if I remember correctly, he said something like, he thinks it feels like it's discovered. And so whatever that means. So, no one knows the answer to this. This is this hotly debated topic, but I think, a lot of mathematicians feel like it's discovered rather than invented. And a famous person by the name of Erdős, definitely, he said there was a book that sort of God keeps where the good math is. And, that's one for the book, kind of thing. So, so that would be discovered in that sense.
The next one is, are you saying that AI can teach us how to think about problems in novel ways?
Oh, absolutely. So I have discussions with GPT a lot about very subtle and sophisticated concepts. I can talk to it like it's a colleague. I tell it. So it performs better if you ask it to role play. So some people I know, like people say, oh, I can't do this or I can't do that. I'm like, treat it like a child. Tell it to show all its work and to work through all the steps, and then it will usually do much better. I can also sometimes, I'll ask it, pretend you're my colleague in the computer science department at an Ivy League university who specializes in transformer architectures, and we're collaborating on a research proposal, and I want to brainstorm some ideas. It does really well, I have to tell you, much better than conversations with some of my colleagues. So, and I'm not picking on computer science specifically, but it's extremely helpful. And my students use it like crazy to get deeper insights. I'm amazed at what a force multiplier it is for them.
Last question here is, why can't AI figure out how to do its computations using less energy? The human brain operates on about the energy of a light bulb. AI consumes a huge amount of energy and is unsustainable from a climate perspective.
Yeah, of course. That's an excellent point. I often think of this as, yeah, it's obscene, right? I mean, you basically are powering these enormous data centers off of the dead bodies. Like, it's scary to think about it. It's like the dead bodies of countless microbes and plants and everything to create the fossil fuels that drive these data centers so that it can gobble up the sum total of all of our hard work, so that it can then leapfrog past us. It's like, it's almost, as I said, deeply disturbing when you think of it that way. And the point is, clearly there are better ways to sort of approach this problem of creating an AGI, because clearly, we do it with 60 watts, and we see almost no tokens in our life. Like GPT sees all of human understanding as part of its training set, all of human knowledge, and we see very, very little from in our classroom and in our interactions. And somehow we're able to do things quite remarkable when you think about it in comparison. Okay, so there's this really where do the instincts figure into it? I remember when I used to live on South Hill, I would see mama deer come in the backyard. I'd be watching out the kitchen window with my kids, and mama would like lay down, and soon Bambi would be out. Okay, and so then Bambi is there laying on the ground. She'll kind of lick it a couple times, and a minute or two later, Bambi's struggling to get up, and it's up. And then it's kind of taking tentative steps a minute or so after that. And then 2 minutes later, it's running. There was no time to learn. It knew up was up, down was down. That's mom, and I'm going. You know what I mean? And there's clearly something inside the hardware of our brains that makes things more efficient. But we don't understand that either. So it's just mystery for mystery on top of mystery, right? It's very exciting to ponder these things.
Are there any more questions from the audience here?
John, good.
The examples that you listed in one of the slides, the one that I find in some ways most intriguing is weather prediction.
Oh.
And the reason that I find it so intriguing is that we've invested enormous computational resources and effort into producing good weather predictions and have made significant progress with it. The fact that the AI can produce similarly good predictions with much less computation suggests to me that there is enormous structure in the atmosphere and the way it operates. Do you think that we can really discover what it's doing in that example as a way of making progress?
Yeah, that's a great question. John, I don't know. I mean, I do know if we don't. Oh, so the question was, given that there are these AI tools that are capable of making weather predictions that exceed the accuracy of, let's say, the first principles models that require very large computing footprints. This seems to imply that maybe there are subtle patterns and connections that have escaped our attention that maybe the AI has learned. And I think that is entirely possible. And frankly, I don't know how else it would be doing it if it hadn't noticed something remarkably simple, right? And the question is how to extract that a posteriori. And sort of this goes back to this idea of trying to use mathematics as the means for understanding how the machine is reasoning. The problem is that these AIs that you're talking about, John, are not made that way. They're not made like the Sci AI way with the math that would allow for that. They're made with the usual techniques that are hard to interpret. And so it kind of goes down to this idea of trying to do stuff, viewing it as a physical system and trying to find patterns and back out what it must be doing. Even though we can't tell precisely that it's doing X, Y, or Z, it must be doing something like this. Let's figure out as best we can through this lens if it's working in this way or working in some other way. But a general transformer-like architecture like GraphCast is just hopelessly complicated. It's like this times a billion, right? And you just to know precisely what's going on in those neural circuits is a very tall order. So I wish I had a better answer for you, but I think it's learned something and clearly has, but can it explain it back to us? And it could be that with some of these large language models, like if this GraphCast isn't a language model per se, but if it were part of one, maybe it could explain to us in natural language what roughly it's doing, right? It's possible.
Any other questions?
I'm curious about the parameters and materials that are fed into AI systems. The idea that you'll get out of what you put into it. And word of warning, my background is librarian, so I'm thinking about materials, information sources that may be only in print, or maybe not in paywall, or having copyright issues.
Yeah, so the question is, where did the data come from that train the networks? And is there really a complete sampling, because some of those data are locked in the form of imprint books or behind paywalls, for instance, journals. Elsevier is holding everything hostage and so forth. And that's a great question. And I think companies like OpenAI spend lots and lots of money to gain access to proprietary data sources, specifically because this represents the special sauce that makes the model work better. So they do try to tap into things that are not widely available to competitors to improve the quality of the training corpus to make the model perform better. And there's less and less of that available these days because these models ingest enormous quantities of data during a training run. It costs something like $100 million in electricity to train a foundation model from scratch, a state-of-the-art foundation model. So tens of millions for sure, but the belief is it's approaching 100 million, and no one will tell you for sure. But that's a lot. That's an insane amount of money just to train a model, and so you need a vast amount of data. And now these models, as big as they get, there's worry that we're sort of running out of data. And this is one of the open questions. What do you do then?
So, with something like the weather models, do they always work? I mean, if you've got one that works today, will it work in a month's time? Does it sort of fall apart?
I bet John probably knows the answer better. So the question is, do the models work well? Do you mean, do they work in every 10, are all the 10-day forecasts equally good? Or do you, yeah. My understanding is they are. My understanding is that they are really, really good on an individual basis. But when you get too much further, this rollout time, past 10 days is a really tough nut to crack. And I don't think anything really works. If, that is kind of one of those things about chaotic systems, there's going to be some point where you're not going to be able to make the prediction. But as far as I know, and John, you may know better, but I think they're really good. Everything I've seen, they've gotten the attention of DoD, complete and utter attention of DoD on these weather forecasts, because those are a huge deal for the Navy. So they're.
Time for one last question.
So if you join AI with quantum computing, what do we get?
That's a really good question. So if you join AI with quantum computing, what do you get? Something super scary. But beyond that, I think quantum computing is, as far as I can tell, and I don't know much about quantum computing, but it seems like it's a pretty niche application space. So the types of problems that you would tackle with a quantum computer seem to be quite special. And the general purpose compute that you would use in these AI systems is something that's a little bit different. The algorithms, so you have to create clever algorithms in quantum information systems to be able to do the computing. And those types of algorithms don't really show up in the calculations that we're talking about in the architectures that are up on the screen. So I'm not 100% certain that there's a huge opportunity for quantum computing to help with AI, but it doesn't mean it's not on the horizon sometime, that there's something brand new. And the really scary thing is the AI systems designing themselves. So they're already being used in designing microchips. Like from everything, when I talk to people who work at Intel and AMD, apparently you can't design a modern microprocessor without very powerful AI tools to help with the process. And so it's kind of interesting that the AI is helping to design the substrate upon which it exists. And there's going to be a time, and Sam Altman says his goal is to essentially have an AI so powerful that it replaces the entire research footprint of OpenAI. So in other words, the AI is doing all the AI research at OpenAI. And then, you sort of see this as what something approaching a singularity or some sort of perpetual motion situation, but who knows?